Hello everyone, my name is Zachary Heidemann. I'm one of your DB team leaders this week. I'm going to be going over problems 1 and 2. My group members are going to be going over 3 and 4 for you. Okay, so number 1, starting with part A. I'm going to show you the problem statement real quick. Let me just copy it. Okay, so we have our problem statement which states that we need to find a binary value for the base 10 value of 24. So 24. Basically what I'm going to do is I'm just going to divide this over and over again by 2. That's the most intuitive way to do it in my opinion. And then we have to write our remainders here too. So 2, 24, 12, remainder 0, 2 into 12 also evenly 0. You can also think of this as a mod operation. So I guess I could do the modulus a function too, but I think this is the most intuitive. So that's also remainder 0. 2 goes into 3 once, but there's a remainder of 1. 2 does not go into 1, so there is left over a remainder of 1. Now I can continue on this operation, so I can go 2 into 0, but that's going to be remainder 0 because it doesn't go in at all. And I can keep doing that forever and add another 0 up here if I wanted to, but that's not going to change the value. So this up here is going to be our most significant bit. Down here is going to be our least significant bit. And now if we chain those together with our unnecessary 0, we have this value, which represents our base 10 value of 24. Part B. Part B basically says we have to do the same thing except going in the opposite direction. We need to take our binary value of 11000 and turn it into our base 10 value of 24. So all we're going to do here is kind of take the place value and multiply that by the current digit that's there. You know how in base 10 we have our place values, ones, tens, hundreds, thousands, but it's the same thing for binary, except we're going to multiply each of these values by its weight. So this 0 here, we have a weight of 5. So we're starting at 0, 0, 1, 2, 3, 4, and 5, which would be right here. So what I'm going to do is write my 0, 2 to the 5th, and then we cascade that down for my 1 for all of our values. And now all of these with a 0 in front are obviously going to go to 0, right? So we don't need to worry about those. And then for these, we're going to get a 16 plus 8, which is, what do you know, 24. Magic. Part C. Now here's the fun one. This is the one I saw the most variation in the discussion board. Most of you had a good function. It's just we didn't display the iterative nature of the function. So the problem is obviously we need to find an encryption function, basically showing how we did part A in a more algorithmic and mathematical way. So most of you had something along the lines of this, which is straight out of our lecture. But with this doesn't tell me how many times you need to iterate through it. See, if I gave somebody a value for Q and for A, then for example, if I put in my value of 12 in for my Q0 and a value of 0 into A0, or A naught, as should be the correct way to say it, I would have 24. But then that doesn't really tell me much because that's not the full process here, right? So what we're going to do is cascade this down, right? So I'm going to take my Q0 after this. The goal here is to show that you need to continue this operation until Q equals 0. So I'm going to show a few of the statements, put a little ellipsis right there, and then put while Q does not equal 0. Okay, now I'm going to put A to the n because this is going to be our value, right? A to the n minus 1, dot, 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 A to the 0. This is to show how you write the answer. But this is telling whoever is reading the function that I need to continue this operation, this process, this pattern, this algorithm until Q equals 0. Okay, so part D. Just get a new layer here so I'm not clogging up. Oh, that's blue. That's not what I want to do. Okay, so D. Oh, I'm still on black, that's fine. There we go. So part D wants us to do something also very similar, which is find a decryption algorithm. So for this one, I'm going to use the summation, but you can also use a sequential function. But I'm going to do the summation for this one and this a sequence for the next one. So our inverse would be as follows. We have our summation symbol. That's a horrible summation symbol, I'm sorry. Starting at 0, and then our n subtracted from 1 because we're going to start out with 1 for that, but we want actually to start at 0. And then we take our a value, whatever place value we're at, so n, which is represented right here, and we multiply that by the weight, which is also 2 to the n. Alright, so at 0, we are going to get this value right here. Then we just move up the value from there. Okay, now let's go on to, let's switch colors here, because we can do that. Let's do purple, that sounds cool. So number 2, part A. Number 2 is very similar. I'm going to grab it for you guys real quick. Number 2 is very similar. Starting with part A, we have to convert the base 10 value of 24 into octal. And that's the same process as we did in number 1. We just have to divide by 8 over and over again. So if I have, take 8 here, 24, that goes in 3 times. No remainder there because that's even. 8 can't go into 3 at all, so that's 0, remainder 3, so our value for octal is 30. Part B would be converting this C value we obtained back into our base 10 value of 24, and that's the same thing we did in question 1, is multiplying each digit by its weight. So we have our number 30 right here. And what I'm going to do is multiply that by its weight, which is in the first spot, 8 to the first times 3, plus 8 to the 0 power, which is going to be 1, times our value. That's going to go to 0, so that doesn't matter, but 8 times 3 is 24, and that was our original value. Part C, we have to find a function for that process, and that's going to be very similar to our number 1, which is simply going to be our n to the, except for the 2 though, we're dividing by 8, so we have to change our 2 to an 8. Q naught plus A naught, and we carry this process through. Oh, I forgot my 8. You see, these problems are very recursive in nature. Wow, Q does not equal 0. We have our solution. Okay, part D. This is where I'm going to show the way you can do it with a summation. Not a summation, I just did the summation. What am I talking about? How you can do this with a sequence. A lot of people chose the sequence. Both answers are right. You can use a summation or a sequence. It kind of conveys the same thing because you have to add up all the values. So the way to convey this with a sequence is you take your remainder, which was your place value. So for us, we have our we have 30. That was our value, right? So I'm gonna write that in here so I don't forget. So basically, we're gonna take our remainder, which is 3, but in general, we have to do this generally, right? So a to the k times 8. You know what? Actually, you know what? K is fine. Times a to the k, and then we add that to k minus 1. A k minus 1 times 8 to the k minus 1. And then we carry this on until we reach a 0 times 8 to the 0, which is just going to be 1. So that won't affect our value. But this is the way to display this with a sequence. All we're doing here is basically what we did in our first problem here. You see how we multiplied each value by its weight. All we're doing with this is just displaying that with a more general approach. So yeah, that's pretty much it until we reach our last value, which would be A naught. Again, this is Zachary Heidemann. This is problems 1 and 2. I hope this all made sense. That's it.
Hello everyone. Today we are going to be looking at week 8's discussion board question from question 3. And let's just start off by going to part A. So here we are asked to convert 24 in base 10 to base 5. There are a couple ways to do this, so I want to show you the first one, and we can build on it in part C. So this we're going to be using repeated division, and the way this works is we're going to take the remainders from multiple repeated divisions and continue until the quotient is 0. So here we have 24, and we know that is equal to 4 times 5, that's 20, plus 4. So that's going to be 24, that works. We're going to take note of this remainder. Then we have 4, which is our previous quotient, and we are going to set that, and we're going to know that that is equal to 0 times 5 plus 4. And now that our quotient is 0, we're going to take our 2 remainders, and that is going to be our answer for this problem, 44 in base 5. That is going to be the base 5 representation of 24. Moving on, we can continue to the decryption part, which is part B. Here we are asked to decrypt our base 5 value back into decimal. So basically the way this works is we can take, well, you know how you can take 24 and that's 2 10s plus 4 1s. We can do a similar thing in base 5. So 44, the value we got earlier, is 4 5s plus 4 1s. And so when we multiply these by their respective place numbers, or weights, and we add them together, we get 4 times 5, that's 20, and 4 times 1, that's 4. So it's going to be 20 plus 4 is 24. So that is the decryption from 44 to 24 in decimal. Moving on to part C, we are asked to get the general case of the encryption algorithm. So we need to convert some number p to base 5. So like I said in part A, we're going to use several methods to solve this, so let's just get started. The first part is the repeated division, just like we did earlier. So the way this works is we have a string of digits that we're going to use as a representation of C. AK minus 1, dot, 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 all the way to A minus 1, A1, where AN, or N is anywhere between 1 and K, that's going to be the remainder from dividing AN minus 1 by 5. And we are going to set A0 equals to P, and we're going to stop when the quotient is 0. So what does this look like? Well, we're going to start with the following. We're going to have A0, which we know is P, so it's going to be P is equal to 5Q plus A1. So we're going to take this, solve for A1 and Q, and we're going to take a note of both of them. Then we're going to recursively do this, or iteratively, depending on how you want to put it, until we get to AK minus 1, and the quotient in here is now going to be 0. So that is the method for how this ends up working. Continuing on, we have part C, which is the remainder sequence, which we can see that any AN is going to be expressible as P div P divided by 5 to the power of n mod 5. So that is going to allow us to get the nth digit of our string. So we can represent it like this. The final method I want to look at is doing this algorithm as a summation. Well, here we can multiply our previous answer, which is going to be this right here, by 10 to the power of k. Now what does this do? 10 to the power of k represents the decimal weight of our previous answer's digit. Now this means that we are going to be representing each base 5 digit as a decimal digit. We're going to go from k equals 0 to the number of digits in p, the number of digits in c. This right here transforms the digits in p to the digits in c. So this is going to give us a decimal representation of the digits of our base 5 number. That may sound confusing, but what's the basic idea of what it's doing is it's allowing each base 5 digit to be represented in its own place in our number system. Then we're just going to take that string of digits and represent it as a base 5 value. This is just marking that it is a base 5 value. So that is how we can represent c as a function of p to convert p from decimal to base 5. Okay, now we are going to continue on to part D, where we are asked to convert back from c to p. Basically how this works is that we can represent this as the following series. 5 to the power of k times ck, which is the kth digit of c, from 0 to the log of c. So this right here tells us how many digits there are in c, and is going to add them all up, weighted by how much each one is worth. So when we take the k equals 0, we're taking the first digit of k, multiplying it by 5 to the power of 0, which is 1, so we're just going to get c to k. Then going up, we're just going to have 5 to the power of 1 times the second digit of k. That's going to be the 5's place, then we're going to the 25's place, then the 125th place, and so on and so forth. So that is basically how this works. We just have a series adding all the digits up, weighted by what their place value is. Hopefully this helps. Now on to question number 4.
Hello class, my name is Michael, and I'll be tackling question 4 with you. So let's begin. The prompt reads, not all functions are invertible. For example, suppose c equals f of p equals p mod 5. Using p equals 24 as your example, explain why the following is true. After converting it to its unique c value, it's impossible to find the decryption function p equals the inverse of f of c. So what's the prompt really telling us? It's just stating that if we start with some number, 24 in this case, and we perform the modulo operation on it, we can convert it into another number, but once we get that new number, there's no way to really convert it back to the 24. So why might that be? Let's start out by solving this one. C equals f of p equals p mod 5, and when we substitute in 24, we get 4, and that's because 5 times 4 plus the remainder 4 equals 24, and we're after this 4 here. So performing this function here, we can convert 24 into 4. So we've encoded 24 to 4. Now, let's ask ourselves, if we start with this number 4, and we didn't know the 24, how might we actually get back to it using some inverse of this function here? And whether or not that's possible, we'll figure out. Well, let's start with an example using a linear function just to show that there are ways to find an inverse function. So we have f of x equals 2x plus 4, and I chose x equals 5 for our example here. So if we plug in the 5, oh yeah, I forgot. We're going to replace the f of x with the y here, and that's just to make it easier to look at. So let's go ahead and plug in that 5 now, and we get y equals 2 times 5 plus 4 equals 14. So our y value equals 14 when x equals 5. Now suppose we don't know that x equals 5, but we still have this function here, and we know that y equals 14. To figure out x, we just solve for x, which gives us y minus 4 over 2. And we know that y is 14, so if we plug that in, we can see 14 minus 4 over 2 equals 5. And that's the x we knew to begin with. So we could see here both functions, here's f and here's the inverse of f. Now, the problem when we return to p mod 5 is that it's not the same as this situation where there's a one-to-one relationship. And that's a big problem because, as we can see here, when you get a remainder of 4, there's multiple, actually infinite numbers that can give you that remainder 4 when you perform the modulo operation on it. So 4 mod 5 equals 4, 9 mod 5 equals 4, 14 mod 5 equals 4, and 19 mod 5 equals 4. We can go on. And we can see here that 24 is one of our answers. But there's really, you can just see that there's no way to choose this 24. There's just no way. Now, that would go on for eternity. And there's another way to actually look at it, and we can consider it like this. So we have an input of 4, 9, 14, 19, 24, 29, yada, yada, yada. Now, we'll perform mod 5 on all of these, and the output will be 4. And this is a valid function because each input has a single output. However, oh yeah, fancy arrows. Now, if we try to do the same, let's pretend there's a function out there where it's the inverse of this modular operation. Now, what we find is that 4 can actually equate to all of these numbers. And as we know, a function cannot have more than one output for a single input, and that pretty much makes it not a function. And so the big problem here is that there's no one-to-one function, and it would just be impossible to determine what input was actually encoded to 4 with just that mod function. So I hope everybody learned something. I sure did this week, and thanks for listening along.